All right, so we're going to spend today and probably the next few episodes discussing the standard model of particle physics. And this is something both Zach and I wanted to dig our brains, get them, get them able to bite a little bit more out of it than what I've done in the past. So I got to dig in a little bit deeper than before.
Yeah, me too. I mean, I'm definitely not a particle physicist by any means. I never even took, like a particle physics or nuclear physics class. So all this is pretty much new to me outside of what I've seen on a PBS special or something.
Yeah, that's pretty much the same story here. Everything I've ever done has been experimental physics. And I find it really interesting at how much I really enjoy particle physics. But it's also interesting whenever I would look into books and stuff, they would always have chapters or sections on the experiments, like how CERN works and like the detectors. And I just flipped through it. I'm like, I don't care. Move on. I want to hear what's going on with the particles that they found and stuff like that. And I didn't care about the experiments in this, this portion of my research into it. I don't know if you felt the same way, but
I mean, it wasn't. I definitely want to look into some of them more than I'm still on an ongoing basis reading about this. I kind of read a book that kind of gave an overview of it, and then maybe I might, dig into little bits here and there. But I was kind of just more about the overview picture where it touched a little bit on, these experiments, but for the most part, it was more like what you've described. And there were some that I thought, hey, maybe that would be interesting to read further on, but I haven't yet.
Right. Yeah. So I guess a good place to start is, what is the standard model? Why do we have it? What is it? What isn't it?
Right. So the book that I read is called The Theory of Almost Everything.
Okay.
And the reason it's called that, it's about standard model. And at this point in time, the standard model has pretty much taken the forces that we knew about and turned them all into one, except for gravity. So, the big thought is, the big goal in physics is to unify the four forces in one single theory. We don't have to, have these two competing quantum QFT type stuff and gravitational, what's the word I'm looking for? General relativity.
Right.
We want one theory for all of that. And the standard model is pretty much as close as we've gotten thus far.
Right. Yeah. So just to be clear, the four forces, there are only four forces in physics right now known. We have the electromagnetic force, strong force, the weak force, and gravity. So in the standard model, we have electromagnetism, the strong force, and the weak force. Those three are covered within the standard model. And then the fourth one, gravity, it doesn't fit into the standard model at all, basically. And it's presumed to be there if there's some sort of quantum version of gravity, but that's a pretty active area of research. And right now we've got nothing. So it's not in there yet, but we've got the other three all covered by the standard model.
Yeah, and I think it's interesting to note that we started unifying forces back in the 1800s with Maxwell. He was the first one to do this with, we had the theory of electricity and the theory of magnetism. And, Maxwell cranked through all of his math and ended up with the theory of electromagnetism. He combined those two into one. And kind of since then, we've said, oh, can we do this with everything? Mm-hmm. And so we're working at it. We've been adding forces throughout the years.
Right. Yeah, there was unification before that even, but we don't really think of it like Newton unified gravity in the sense that the things like apples falling out of the tree and the moon orbiting the Earth, those are two separate phenomena until Newton's like, wait a second, what if they're the same thing? So he unified, I don't even know what they were called back then, apple falling force and moon orbit force. So
yeah,
that was another unification. Yeah. But yeah, usually we start with electricity and magnetism unified by Maxwell. And then from there, we started building on other unification theories. And we definitely have electricity and magnetism into electromagnetism. And then electromagnetism and the weak force have been unified as coming from the same source. And now the strong force, it kind of is unified, maybe at certain energies sometimes. if you look at it in the right direction, but it's not perfectly unified with the others, but it's at least encompassed by this standard model.
Yeah. I mean, at this point, my understanding is we're fairly comfortable calling it the electroweak force, meaning electricity, magnetism, and the weak force as one force. But the strong force is encompassed in the standard model. But yeah, I don't think I haven't read yet that it's, completely unified.
Yeah.
As well.
Right. And we'll get to the history of it. And when, in particular, we start talking about beyond the standard model, one of the things that they're trying to do is get the strong force perfectly lined up with the electroweak force so that they are actually unified. And there's ideas on how to do that. But within the standard model, they're not perfectly lined up.
So,
go ahead.
Is the standard model, I'm just going to ask you, is the standard model only about forces or?
Well, it's forces, but the forces got to do something. So it's also about what the forces act on, which is the particles. So we have the forces interacting with the standard model particles. So we have a collection of elementary particles, meaning they are not made of any constituent parts as far as we can tell. Like these are the basic building blocks of matter, actually. Not atoms, but even smaller than atoms, not nuclei, smaller than nuclei. And so this is all of the quarks, which we'll talk about, and all of the other things, leptons. Yeah. So we'll talk about what those are, but we got quarks and we got leptons, and that makes up the mass. Everything that has mass basically is made up of those particles. Everything you touch, everything you interact with is really like 3 of those things, but there's a whole slew of 12 that make up everything possible in the universe. Every nuclear reactor, every particle collider, every, intergalactic, whatever you want to come up with in sci-fi. As if it's based in our understanding of physics, it's made up of those 12 particles.
Yeah. The standard model is like, it's got to be one of the most ambitious things like ever attempted by humans, right? Just to say, hey, okay, we want to take all the forces, unify them into one, and we want to figure out the bare minimum number of things that we need to make up the entire universe. Like,
what are the ingredients to cook up a universe? Yeah.
Yeah. And, we're pretty close. Like we're getting there.
Yep.
And so, I think the standard model is our best explanation of this so far. And it's also one of our most accurate.
Right.
The theory can predict to a high degree of accuracy experiment.
Yes, that's right. I was going to add that I've seen in doing this research, obviously spent some time Googling the standard model, and now my Android phone gives me recommendations of articles when they come up talking about the standard model. And I guess something was written kind of recently where somebody was claiming that the standard model is a tyrant and it's a big jerk in physics experiments because there's like basically it's done, which is totally, a false way to look at physics and in science and advancement. But he's making a point that the standard model basically is complete. And so looking for other stuff, you're not going to find it because it's not in the standard model. So he's not saying don't even try. He's just saying like it's pretty boring out there because standard model is pretty much dead on correct at every place you turn.
Right. And I've heard so the Higgs boson is part of the standard model.
Right.
And before we found it in 2012, one of the things I heard is that a lot of people working at CERN were hoping we didn't find it.
Right.
Just because then life would be interesting for physicists.
There'd be some interesting new physics. And, they found it. And what was its mass? Smack dab right in the middle where the standard model said it would be. So it's like, yep, that's exactly what it was. Yeah. And one of the books I was reading called The New Cosmic Onion, which I almost didn't check out of the library because it's a stupid title, but it actually is a pretty good book. And the cover has an onion with layers being peeled back to little atom pictures, which is stupid, but whatever.
Did Shrek come first or did that book come first?
Yeah, it's the donkey. The donkey wrote it, but it should be The New Cosmic Parfait.
Yeah.
We're going deep in the Shrek references. But he says, he has a whole section called why 1 TeV of energy, which is what CERN produces in its particle collisions, is those interactions are happening at 1 TeV of energy. And he does a nice 1-page derivation showing the Higgs should be at this mass, and to get to that mass of particle, you need to have protons moving at 1 TeV worth of kinetic energy. So I thought it was a pretty neat little one-page proof as to what, and the book was written before the Higgs was discovered. And so he's saying the mass we expect to be about here within this range. And to get there, you need 1 TeV of energy. And that's what CERN was built to do. And it did it.
And there's been a lot of like instances of that. Like I think at some point we might talk about pion, and that was a particle that was predicted to exist with like these rough, properties. And lo and behold, we found it, and it was, it matched all the same properties. And then I think it happened again with Murray Gell-Mann. I forget what the particle was, but to get his symmetries right, he predicted there'd need to be another particle, and then we found
omega.
it. Yes, that was it. The omega minus is what I think.
Yeah. And yeah, exactly. It's in a lot of people draw the parallel between the standard model and the periodic table in chemistry, and saying you can make predictions based on it of where particles should be and what the properties are before anybody even knew the particle existed. You can look at the symmetry and the just organizational structure of these particles and say, there's something missing. It should be right here, and it should have this property. And then boom, they find it.
Which is something that I think Mendeleev, I believe that's the guy that created the periodic table, that he did as well, because once he organized it all, he found gaps and just said, oh, hey, I think, we're going to find an element that has this number of protons in it. And then we did.
Yep. So why don't we get into it and just give the overview of what are these particles that we're talking about? There's a few ways to break it down. And I should say this is completely done. The standard model is organized in hindsight, with the particles being discovered in piecemeal and then eventually organized into a nice structure that we have today. But, we knew of the electron well before the standard model existed, right? But that's one of the fundamental particles, the electron. So that's one of the 12 stuff that makes up all of matter in the universe. So electron, you can check it off your list. Done. Found. Understood. But the lepton's an example of, well, we could break it up into the things that make up the matter, the fermions. So we got fermions. That's the stuff that makes up everything you touch. And then you have bosons, which make up all the forces and all the particles that do the forces, basically, interact with things. They're zipping back and forth between all the matter. Doesn't mean that these force particles are massless. It just means that they don't make up the stuff that we interact with day to day. They can. There's some theories that say they could, but really the stuff, stars and desks and computers, those are made up of fermions, and then the way they all interact with each other, bosons.
So do we want to give the difference between those two things?
Sure. Yeah, the basic fundamental difference is the way that spin works in both of those different categories. Fermions, which make up the matter, are made up of half integer spin. So it could be a spin of 1/2 h bar, or it could be 3/2 h bar, not 2/2 h bar, which would just be h bar. So it's odd numbers over 2. That's basically the spin of these particles. So it's a quantum mechanical property, and the way it works, the reason that's important is because when they have half integer spin, they obey the Pauli exclusion principle, which gives very, very different physics than when things are integer spin, which the bosons are. So bosons can be a spin of h bar or 2 h bar or 12 h bar or 0 h bar. Those are bosons. And that's really the dividing line, is what is their spin? Look at that. If it's an odd number over 2 multiplied by h bar, it's a fermion.
I mean, yeah, I guess the only thing I'd add is essentially what we have is in the Pauli exclusion principle is, we can't have any two fermions occupying the same quantum state at the same time, which, leads to essentially all of chemistry.
Right. I should add and clarify, because electrons are fermions, so they're one of those particles that have a half integer spin,
right,
and they are going to obey the Pauli exclusion principle, which ends up building up the elements that we see in the periodic table, the way that we see them. So why does oxygen have a valence of 6, or whatever? Helium's a noble gas that doesn't interact. All of those properties basically come from electrons being fermions following Pauli exclusion principle.
Yeah, I mean, all of chemistry is just how these electrons interact with each other. And it's all based on this exclusion principle. And then bosons, on the other hand, you can have an infinite number of bosons in the same quantum state.
Right. So those force carrying particles, they can collapse in on themselves and exist in the same little bin, quantum mechanically speaking. And you can fit as many as you want. They're happy to be there. No exclusion principle for them.
And so that's kind of like the first breakdown of these things. And then so we have, our set of elementary particles, we have, a group called fermions and a group called bosons. And then each one of those break down into smaller categories.
Right.
Where the fermions break down into kind of quarks, antiquarks, and leptons, antileptons. I don't know. Are we talking about antiparticles?
I haven't said antiparticle, but yeah, everything we say, you can take you can double it, and then there's the anti version of that. So every electron, there's an anti-electron, which has its own name. It's called a positron. I don't think there's any other ones that have a special name. No, they're just anti whatever. But then the electron has a special name, the positron. So all of this has antimatter versions. The standard models particles all have antiparticle versions of themselves. So you can double everything in the standard model.
Right. Yeah. So we have these classifications of beneath fermions, we have two types. We have the quarks and the leptons. Mm-hmm. And then they're antiparticles. And they both have spin 1/2. So, okay, there's got to be a dividing thing between them. My understanding is that quarks have a thing called color charge, whereas leptons don't have this color charge.
Right. Quarks interact through the strong force. It's possible for them to interact through the strong force, but the leptons do not interact through the strong force at all. So the strong force carrying particle, which we'll get to in a bit, doesn't touch leptons. They don't even see it.
Which is color related. I think color is an interesting thing to we don't have to go deep into it, but everyone's like familiar with electric charge. Like that's something that we deal with fairly regularly in our life. Everyone deals with it regularly, whether you know it or not, but a lot of people understand that they're dealing with it. But like color charge, what is that? It's a whole other...
Right.
It's not called color because it has anything to do with the actual color of quarks.
Right.
It's just another property, and color was a good analogy for this. But we could have one of the books I read said, we could have called it gender, where we could have had the gender charge with he, she, and it being the three charges. In our case, we have color with red, green, and blue.
Right. So we needed something with three. It comes down to having a split into threes. Charge, we have positive and negative, like essentially splits into two that are opposites of each other. But color, we needed some way to distinguish three different things. And so, someone came up with red, green, blue. That's kind of a nice triplet thing that we're all comfortable with. They mix together in a certain way to give you white. So that was what physicists came up with for this triplet, this way to split a group into threes. So quarks have color. Leptons don't have color. And strong force interacts through color.
Yes.
So quarks, leptons, we can just list them. The electron is one lepton we've already covered. There's another one it's the electron, and then two more that are heavy versions of the electron. Like they're pretty much the same thing. They're just heavier. And that's the muon and the tau. So they're almost identical. Like an electron and a proton can get together and make hydrogen. You can put a muon with a proton and have a weird version of hydrogen, and it totally works. Different states, but it's possible. And then the next one after the muon is the tau particle, which again, it's just like the electron and the muon. They all have negative charge equal to the electron's charge. It's just different masses for all of them.
Yeah. So, I mean, I think one of the things we could be clear on right now is I think there's generally, we are categorizing everything now by these very few properties. We have spin, which we talked about,
right?
Electric charge, mass, and color charge,
right?
And so Derek is saying that it's the same thing but heavier. What he means is it's a particle that has the same mass, does not have the same mass, has the same spin, same charge, same color charge, meaning no color charge for these particles. But the only thing that's different between them is the mass.
Right. And the book I was reading, the Cosmic Onion book, it kept referencing how the Higgs essentially messed up all the symmetry of these particles, because these particles have mass, as you probably have heard in pop articles and news stories. With the Higgs, is that the Higgs gives these particles their mass. Through the Higgs interaction, these particles gain mass. And so the fact that the only difference between the electron, muon, and tau is their mass, you can basically attribute to the Higgs. Otherwise, these would just be exactly the same particles and just very happy to all collapse down into one particle thing. So the Higgs, we'll talk about symmetry breaking probably when we get into the weak interaction, but it's messing up this beautiful symmetry of these three things being the same. It just is like, well, now we got three different kinds because the Higgs likes to interact differently with them. Yeah,
when the muon was discovered, actually, I think the physicist's name was Rabi, I think. But one physicist was famous for noting when they discovered it, who ordered that is the big quote, because, why do we need a particle that's exactly the same as the electron, just a little heavier?
Right. Yeah, so those are the three leptons that make up, or that don't interact through the strong force, but they make up some of our matter. And then each lepton of those electron, muon, and tau, it has a neutrino version, which the neutrinos are also leptons, but like the electron has an electron neutrino. Muon has the muon has a muon neutrino, and the tau has a tau neutrino. So is it tauon? I don't know why I thought it was called tauon. Now I'm looking at this table questioning my understanding of these things. But whatever. The tau and the tau neutrino. So you got three leptons with their lepton neutrinos paired up with them.
And these are one of the more interesting particles, I think, because I think it's still not quite understood what their mass is at this point in time, right?
Right. But it's not zero, which was the main thing.
Yeah.
Yeah.
I think for a long time, though, it was thought that they were massless, right? Mm-hmm. And then we discovered, these things actually do have some mass.
Right. Oh, yeah. When I was going through undergrad, my nuclear physics book, I think it was Crane, said the neutrinos were massless. And that's how I learned it, originally. And then, within that short amount of time, they found out that it has mass. But that's a fairly recent discovery. And it's just extremely, extremely tiny mass, which is why most people thought it was zero.
And I think we should mention that, within these groups of leptons or whatever we're gonna cover, at least the fermions, we had, like we said, we had the electron, the muon, and the tau, and the only difference is they get heavier. And then we have the neutrino that pairs with each one of those things. Those things are called generations, meaning the electron and electron neutrino are first generation, muon neutrino, second generation, tau neutrino, the third generation.
That's right. Yep. Yeah. And something I learned that I didn't know beforehand was that the handedness, I guess you could say, I don't know if you want to get into this, but the handedness of neutrinos is specified in the Standard Model as only being left-handed, meaning like the way they spiral, like imagine a football spiraling or something, twisting like a screw. Neutrinos are only in the Standard Model, they're only allowed to be left-handed, like they screw, I don't know, counterclockwise if you're looking at it moving away from you kind of thing.
Huh. Interesting.
Yeah. But what's interesting also is that the mass being not zero means that it's possible to move faster than the neutrinos. Since they are not moving at the speed of light, there's some difference between the neutrino's speed and the speed of light, which is a fundamental limit, right? So you can move faster than a neutrino. And then the book brings up the problem now, since the neutrinos are not massless, and therefore you can move faster than them. If something is spiraling one direction, but say you pass it moving faster than it and look back at it, it's spiraling in the opposite direction. I know you can do the mental flip of like which way it's spinning, but in physics terms, it actually would start spinning the other direction, which is forbidden in the Standard Model. So that is now one of the puzzles of like, okay, so these neutrinos have non-zero mass. That messes up the left-handedness requirement in the standard model.
Yeah, I think that's super interesting, and that's something that we should think in a future episode. We'll delve more into each one of these, and I think that's a thing we can dig deeper into. Mm-hmm. So let you know kind of like what's coming up.
Yeah, we're definitely going to spend some time beyond the standard model, which this now opens up some interesting hypotheses and things to look into.
And also, you might remember the neutrino from, was it 2011, 2012? Somewhere around there, when there was claims of a particle, the neutrino, going faster than the speed of light.
Forgot about that.
Yeah, that was kind of one of the neutrino's shining moments. Turns out, I believe it was just a GPS error, if I remember correctly.
Oh, yeah. I thought it was like a cable was not plugged in properly or something.
Maybe that's what it was, yeah.
They didn't unplug it and plug it back in the right way.
Yeah, they don't travel faster than light.
Nope.
Slower than light, they have mass. But those are all of the fermions, leptons, generations of leptons.
Mm-hmm. So leptons are covered. We got 6 of them: electron, muon, tau, and then the 3 neutrinos. Boom.
Yeah, and all their anti
and
versions.
Then they double it for all the anti-particles. Anti-muon, anti-tau. Exactly. Might be worth saying where the muon and tau come from. Like we make them in colliders, but I think they're first discovered in cosmic rays, right? Like stuff hits our atmosphere and just explodes when it hits another atom in the atmosphere. Like high energy particles leave supernovas very, very far away, fly at the Earth every once in a while, and hit stuff in the atmosphere. And we're able to detect the showers that come down. And some of those are muons or tau particles.
Right. Yeah. Hold out your hand. Parallel to the ground, and roughly going through your palm at any moment in time, I think it's about 1 to 6, somewhere in there, muons per second are passing through your hand.
That's higher than I thought it would be. That's cool. And I've heard that you can make a particle detector and then put it underground, and it's basically a test of how deep under the Earth you are, like because of how many or how few particles it detects. Based on depth. The deeper you go, you're not going to count as many particles.
And, for the rigorous listener, I don't know, the person that's really excited, you can make a cloud chamber. Actually, it's really easy. You just need some dry ice and some isopropyl alcohol in a sealed container, and you can actually see muons. Mm-hmm. There's things online that show you how to make a cloud chamber. You can build one, and you're going to see those cosmic rays going through your cloud. Which
is exactly what physicists used to do. They used to take pictures of cloud chambers and study the paths that the particles made. Maybe they applied a magnet to it and saw how the charged particles curved around, and they can get charge to mass ratios and stuff like that. And that's basically what particle physics was until they were like, well, let's make our own particles. Let's not wait for something to fall out of the sky.
Yeah. I was reading that there's actually like particle physics for a while. It was an adventure sport is how my author claimed it. Yeah.
Because they'd have to go up into the mountains, right, to get the most number of particles. And
so there's a lot of, mountain climbing and like ice climbing. People would fall into crevices and die. So it's kind of crazy.
Cushy physicists these days in their labs.
Yeah.
Wearing hard hats. Something I just remembered talking about the depth detectors with the particle detectors. I think they found a chamber in one of the pyramids in Egypt using this method where they counted more particles than they thought they would based on how much essentially rock of the pyramid the particles would have to go through. And so they figured out that there's actually an empty space inside the pyramid because more particles are getting through to the detector.
Yeah, it's really great. We actually do this lab at UCSB. It's called muon tomography. Yeah, and so essentially, because it's raining down muons from the sky pretty much fairly constantly, you can take a detector that is able to also determine angles and stuff. Mm-hmm. And you just count how many muons you're seeing from which direction you're seeing. And it's a 3-dimensional angle. Mm-hmm. And, if you're seeing a lot from... like you put the detector somewhere underneath a ceiling and you see a lot coming from above you, but not coming from the sides. Then you realize, okay, you're there's a hole above you, and you can detect holes. Or I don't know if this is a practical use of it, but you can also use it to detect things like nuclear weapons. Because the higher the Z of the substance that's above you, the more it gets absorbed, the more likely it is to absorb it. So, like, if you have
higher the Z?
Yeah, the protons, the number of protons.
Like atomic. Yeah, got it.
So, like, if you have a piece of carbon above your muon detector versus a piece of lead, you're going to see way more muons through the carbon than you are through the lead. Mm-hmm. And nuclear weapons happen to just have really, really high number of protons in them.
Right. You got some uranium up there. There's a lot of protons per atom.
Yeah. So you get this really dense, like, hole.
Yeah. You're not detecting much. Cool. Yeah. So that wraps up leptons, and we'll probably come back to them. But I love talking about quarks. I think if I just had to pick my favorite group of particles, it'd be the quarks. I think they're awesome. I think they have awesome names. I think they're just silly. And my book has some funny pictures for them. I almost didn't get the book again because I flipped through and they're just ridiculous drawings for these particles, like little gnome characters and stuff. But yeah, we got 6 quarks, and again, they're organized into 3 generations, just like the leptons, which is an interesting symmetry that people are, one of the ways they're trying to unify the strong force and the electroweak force is like there's probably some underlying symmetry here, like some underlying physics. The fact that we have 6 leptons and 6 quarks is pretty weird. Like, why?
Yeah.
So the main ones that we mostly interact with are the up and the down quarks. And the reason we mostly interact with those 2 quarks is that a proton is made up of up and down quarks, and then a neutron is also made up of up and down quarks. So for your proton, you have an up, and a down. And then a neutron, you have an up and then 2 downs. So you got your combos and up and downs. That makes up protons and neutrons. That's pretty much every atom that we interact with.
Right.
So really, we got up and down quarks and electrons that in your day-to-day life, that covers, well beyond 99.999% of the stuff you're touching and dealing with every day.
Yeah. I mean, it's almost, I think it's pretty interesting that we even found anything beyond that because it's so like rare in comparison.
Right. And it's funny to make it seem, to highlight how I almost said the word, but how weird it is that we found something past the up and the down. The next quark that was found, they called it strange because it was so weird. They're like, why is this particle here? This stuff is acting strange. So yeah, we got the up and the down quarks, and then we have the strange quark, which was discovered next, and the charmed quark. So that's your 2nd generation quark family, charm and strange. And then after that, we got, now we call them top and bottom. But again, I don't know, my nuclear physics book was pretty dated, I guess. We got massless neutrinos, and then the top and bottom quarks were named truth and beauty.
Yeah. Actually, one of the things that I read is Gelman, when he named it the strange quark, apparently, before he named it, before they discovered the quark itself, he had this strangeness property of particles. Mm-hmm. And when he first tried to publish this, the editor wrote back, said, you can't call it that. You can't call it the strangeness, right. And made him change it. But then it kind of won out in terms of the popularity amongst the physicists, in the world. They liked the strange idea, so they ran with it. Mm-hmm. And I think the same thing happened with truth and beauty. Yeah. But then top and bottom somehow ended up winning out.
Right. Yeah. Competing name theories, truth and beauty. And they're like, no. Now we're getting too crazy. Let's go with top and bottom, which is totally not confusing because we have up, down, and then also top, bottom, but whatever. But yeah, usually it's just U and D, and then C and S, and T and B. Those are the symbols for those quarks. So yeah, like I said, the proton and neutron, those are made up of quarks. You can mix up any combination of quarks that you want as long as it follows certain particular rules. One of my favorite things about quarks, like the electron, has a charge of -1, just based on basically Ben Franklin picking the wrong sign for charge, and the electron has one fundamental unit of it, and it's negative. So, oh well, we're stuck with that. But at least it's a fundamental unit of charge, the electron. And the proton, a fundamental unit of charge, +1. But the quarks have fractional charge. And we learned, you probably learned in physics, you can't have less than the fundamental unit of charge. But all of the quarks have either 2/3 or -1/3 of that fundamental unit of charge, which I think is I think it's cool. I don't know. I like the fact that it breaks that rule, but it doesn't, because think about 2 up quarks, each of them having charge of 2/3. We're at 4/3. And then throw in a down quark, and now you got 4/3 minus 1/3. You're at +3/3, which is your proton. Still one fundamental unit of charge.
And quarks are an interesting beast, because we can observe electrons, not like observe and see them, but we can make electrons, and we know that they're electrons. We can isolate protons. That's probably the word I should use. Isolate, and we know they're protons. We have yet to isolate a quark, is my understanding.
Yeah.
And you can't isolate a quark. Yeah.
Right.
So quarks are interesting in that they always have to come in these triplets, such that their color charge is white.
Right. Yeah. You can organize the quarks in any way you want, as long as you have basically, the technical term is a colorless singlet state of quarks. And you got 2 ways to do that. One is to combine a red, green, and blue quark, or some state that's a mixed version that ends up being linear combinations of red, green, blue quarks. The other way is to have a quark and an anti-quark, and that gets you your colorless singlet.
Yeah, red plus anti-red equals colorless white.
White, essentially. Yeah. So you can have an up quark and an anti-up quark, and then that's a valid particle that you could have. And you can also have an up, and a down, as long as it's red, green, blue. It doesn't matter which one's red, which one's green, which one's blue, but as long as they all are considered 3 different colors, then you're good. That particle exists. What you can't have is 1 up and 1 down. Doesn't work. You can't have a particle that has that.
Yeah, one of the things I read was interesting in saying that. So I forget who it was, but someone was being pressed at a conference by an audience member who was asking a question. Like, if you've never seen individual quarks, how do you know that they're real? Mm-hmm. And he responded by asking, like, well, have you ever seen the Pope? And the question asker said, well, I've seen him on TV. And then so the author brings up this point saying that, this question asker has never seen the Pope except on TV. In order to see it on TV, we have light that bounces off of the Pope and goes into some sort of film or camera, and then that gets digitized and then sent through radio waves to another location, and then when that receives it and undigitizes them and shoots an electron ray, but this is back when CRTs were a thing, onto a TV. And so you have all of these like intermediate steps to you seeing the Pope, but you see it and you believe that's the Pope.
Right.
And with quarks, we have all these intermediate steps to seeing quarks, and that's why we believe that there's quarks, and it's actually a lot less complicated than seeing the Pope on TV. And so, like, even though we've never seen one, we can logically follow each step that would lead us to individual quarks.
Right. Yep.
And one thing about them that I learned recently, which is kind of embarrassing, is quirk. Like, hey, you're really quirky, is spelled differently than quarks.
You thought those were the same word?
Yeah, I didn't realize one was an A and one was an I.
Yeah, that's funny. I don't know if this is true, but I think Murray Gell-Mann got it from Finnegan's Wake. And there's like a line in Finnegan's Wake, which is ridiculous to read if anyone's ever opened that book. But basically, James Joyce had a line that said something like 3 quarks, a muster mark. I don't know. Anyway, it had the number 3. And so Murray Gell-Mann apparently reads Finnegan's Wake and decided to name a particle after the 3 quarks, a muster mark.
So, yes, I read the same thing. That's exactly what it was named after.
Yeah. So yeah, as you said, you can't have a quark isolated. You can have groups of 3 quarks, or you can have pairs of quarks, with one being a normal quark and another being an antiquark. This is not standard model particles, but the 3 quarks and quark-antiquark groups of types of constituent particles, I guess you could say, those are other types. Those have other names, which are baryons, which are the 3 quarks, and then mesons, which is the quark-antiquark. I wanted to say that because I was going to drop the word meson, but I wanted to explain what it was first. You can't have a quark isolated, but if you take a meson and try and pull quarks apart, what happens is the force gets stronger and stronger as the things get separated. And it ends up getting to a point where you pull apart the quarks as much as you can, but then if you add any more energy into that system to stretch it further apart, the universe just says, you know what, we don't need to do this anymore. That energy that's holding these 2 quarks together, let's turn that into 2 more quarks. And you rip apart a meson by generating new quarks, essentially. And you end up with 2 new mesons that are made up of the energy converted into mass. And if you had an up and an anti-down quark, you could pull that apart, and then the up quark all of a sudden has another anti-down quark next to it. That's not the original one, whatever. You can tag them however you like. And then the anti-down quark all of a sudden has an up quark paired with it, or some other quarks. It doesn't have to be the exact ones, but essentially the way to think about it is you try and rip those apart. The physics finds a way to not let you do that.
Yeah, and this pulling them apart and getting harder and harder is this thing called asymptotic freedom, which was discovered by 3 people in the 70s, David Gross, Frank Wilczek, and David Pulitzer, I think. But David Gross actually is a professor at UCSB, and that's he won the Nobel Prize for this.
Yeah, you guys probably have quite a few Nobel Prize winners.
I think we're up to 5 at the school. I don't know if you can count all of them, but
some way associated. That's cool.
Yeah. Yes. Yeah.
Yeah. So interesting. Just talking about mass of these particles, quarks are quite a bit heavier than the leptons. With just rough numbers, the quarks are 2.2 MeV. The down quark is 4.7 MeV.
So before you even go on, okay, I think 2 things need to be said. One, what the heck is a MeV or EV? It's a mega EV.
Right.
And
I hesitated because I was like, it doesn't really matter what the units are. Just 2.2 of them and 4.7 of them is what I was going to say.
Right. Okay. Well, I mean, if you want to skip that, we can, but I think it's worth noting that at least in this field, EV is an electron volt. Who cares about that? But the important part is it's a unit of energy. Right. But you just said the mass of these things.
Yeah. And yeah, so it's all Einstein's equivalence, or, his famous equation E equals mc squared, where we talk about mass of particles in terms of the amount of energy equivalents they are. And I should say technically MeV per c squared to get it actually in units of mass. But usually people don't care about the per c squared part because they all have that. So they just say 2.2 MeV.
Right. And if you work in the right units as well, C is 1. So
yeah, exactly. Pick your units so that C equals 1. And yeah, it doesn't matter. Just ignore the C's. But yeah, MeV is mega electron volts. So 2.2 million electron volts worth of energy is the mass of this up quark. And then 4.7 MeV is the down quark. But what's interesting is I said that a proton's 2 up and 1 down. So 2 up would be 2.2. Plus another 2.2, we're at 4.4. And then a 4.7, add to the 4.4, and we are at 9.1, if I did my math right. 9.1 MeV, that's the sum of the quark's mass that makes up the proton. If you look up the mass of the proton, instead of 9.1 MeV, we have basically 100 times that, 938 MeV. I always find that really surprising. I know why, and it's not that interesting. It's just like a weird fact, but it's funny to think like, oh, you just add up the quark mass and that's your proton mass. Not even close. You're at 1% of the proton mass. And we are all made of quarks, up and down quarks mostly, and electrons, which in the same units is half an MeV, so they don't contribute that much. But the protons, we're just add up the quarks and the electrons, we're only at 1% of our mass. So where does that other 99% of mass come from?
Right. Well, I mean, doesn't it all go back to that equivalence principle and the strong interaction? I mean, we have the binding energy.
Yeah. Maybe I shouldn't have said equivalence principle. That's not what that is, but yeah.
You're right. That's true. Yeah.
Einstein's E equals mc squared. Right. So we got a ton of energy, this binding energy that's holding these quarks together that we said is super strong. Try and rip it apart and you just generate new particles because it takes that much energy. Yeah. It's all that binding energy inside the protons and neutrons, basically. That's the 99% of your mass is made up of just binding energy, which is always kind of fun to think about. So we got up and down quarks, charm and strange, top and bottom. And these things get quite a bit heavier as you step up the generation from the first generation of up-down. Up was 2.2 mega electron volts. If you step up in generation, the charm quark's about 1 giga electron volt, and then the strange quark is about 100 MeV, mega electron volts. Again, where the up quark was just 2.2 mega electron volts. So we're getting quite a bit heavier. We're getting quite a bit heavier as you step up in generation. And then the next one up, I'm going to save the heaviest quark for last, but the bottom quark is 4 giga electron volts. And then the top quark, I think it just wins everything by quite a bit. Higgs is just shy of this, but the top quark is the heaviest quark by far at 173 giga electron volts. So we're in the billions, 173 billion electron volts for the top quark compared to the up, which is 2.2.
Which is,
2.2 million.
I think we can note here with all these masses that Derek is saying and energy units, this is why we have to build these huge, giant colliders. In order to produce these things, we have to have energy of at least twice or at least to produce a antiparticle-particle pair, we have to have energy of twice the mass of them. So that's why we have to have, a 27 kilometer long circular large hadron collider. Mm-hmm. Mm-hmm. And actually, I don't think we needed that to produce any of the quarks that we've listed so far.
No, yeah. Yeah, exactly. You just need a ton of energy. And then you also need to get a lot of them. So we could make the bottom quarks in some old particle accelerators, or we would get them out of cosmic rays or something like that. But we wouldn't get that many of them. But what you really want is good statistics. You want a lot of these particles coming out of your accelerators so you can study them well, because, you measure one thing and you're like, well, that wasn't that interesting. I don't know if that was just a fluke or that's actually important, but you get it, millions of them, then it's pretty good statistics and pretty good results, enough to say, like, with confidence that this is actually what's happening physically. It's not a fluke of the statistics. It's not just a random thing that happens every once in a while. And also these particles being so massive, they don't last very long, because energetically a charm quark is much happier being a down quark or an up quark or a strange quark. These quarks decay into the lighter quarks because energetically it's favorable to be at a lower energy than it is at a high energy. So charm could decay, top decays very quickly to the point that it has different physics. Like, you can't make the same particles. You can't make a meson out of top quarks. Like, it just doesn't last long enough for the physics to even take hold and to make a bound state with another quark. So there's funny things like that where you have to play with statistics and also fighting quick decaying of the quarks.
And I think there's another term I want to add in here, because you said what baryons are and what mesons are, but I think the thing we should add is the classification of all that outside of just quarks, right, is, I think, hadrons.
Right. Yes, that's true. Anything that's made of any quark thing is a hadron.
Which is, relevant when you talk about, like, the LHC, which is the Large Hadron Collider. That's what they're colliding are protons.
Quark particles.
Yes.
Yeah. Yep. And so everything basically is unstable until you get to the lightest quark, and then the physics is happy to stay there, which is the up quark. So all quarks can decay into the up quark. And so that means if you have a particle that's up, down, down, which is what particle, Zach? Pop quiz.
Up, down, down is the neutron.
Neutron, yeah. The up, down, down. It might want to decay one of those downs into an up because it can make another particle that follows the rules of physics and is happy to exist. Which is what particle?
The proton.
Yeah. So a neutron is unstable. A neutron decays into a proton. And I think it has a half-life of like 15 minutes if it's just an isolated neutron. It doesn't do that very often inside of nuclei, but it does happen every once in a while where a down decays into an up, which is, we say, via the weak interaction, the weak force. A down quark would decay to an up quark, and then you get a neutron turned into a proton. So you can change elements, essentially, because now you have a different number of protons. That's a different element. But it's all about making these low energy states, the lowest mass, lowest energy particles. That's the happy place.
One of the things I read too is that I think this is kind of one of the older theories, but you can describe proton-neutron interactions by an exchange of quark-antiquark pairs, and it turns one in, or maybe that must not be a pair, but quarks and antiquarks that changes one proton into a neutron and a neutron into a proton, and that's how you can talk about the forces between them one way.
Yeah. Something that came out of this book that I wasn't aware of was we got the electromagnetic force, and we'll talk about what particles mediate that. Basically, you got particles whizzing back and forth between charges, but then you have nuclear forces, which is what is interacting between protons and neutrons inside an atomic nucleus, which is separate from the strong force, which is what holds the quarks together. Up until this book, in my head, for some reason, I just have never studied this, I guess. My assumption was that protons and neutrons exist in the nucleus as kind of a quark soup. I didn't know if they were actually individual particles. I know they were because they're bound together in these colorless singlets. But I thought it was the strong force holding protons and neutrons together. Or sorry, holding protons and neutrons not together in isolated particles, but together in the nucleus. It kind of is, but they're mediated by some particle you said earlier, which is the pion, which is an up quark. See, a pion? Yeah, an up and down quark. One of them's antiparticle of the other one, or it's some combination of up and down particle antiparticles. But the pion is the thing that's whizzing back and forth inside of a nucleus between protons and neutrons. I didn't know that. I don't know why I thought it was the just basic strong force particle.
Yeah, I guess I didn't quite connect those dots either. That I read that there's that interaction holding the neutrons and protons together, but I guess I didn't realize that that's not equivalent to the strong force.
Yeah, that same with me. I don't know why I've never encountered that anywhere. Maybe this is just the way this guy's organizing the forces, but he kept saying it, and then he actually made a table. He like outlined it in a table form that said electromagnetism, nuclear, strong force, and nuclear and strong were two different forces. And the pion was the one that worked in the nuclear force. And I thought that was weird. But he kept talking about it. And actually, after he said it, I saw in other books also. So I know he's not making it up.
Right. Yeah, that's what I saw in my book. But I guess I kind of thought they were referring to strong forces, but I guess not. Interesting. Mm-hmm. I misunderstood.
Yeah. I mean, it is at some level, right? I mean, it's a pair of quarks that are bound together through the strong force interacting with other quarks that are bound together through the strong force. But yeah.
Yeah. Okay. So I think that was enough hadron and lepton talk, or fermion talk in general.
Yeah. Covered all the fermions, 12 of them. 12. We got 6 leptons, 6 quarks, and then double it for the antiparticles. But yeah.
And did we say that the antiparticle is the same particle just with different electric charge? Is that right?
Yes. And there's things like strangeness. Like you said, Gell-Mann was coming up with, quantifying things, and there's some rules that are roughly followed, but in some situations it's not followed, like conservation of strangeness. So if you have a strange quark, its strangeness is, I think it's actually, a strange quark has a strangeness of -1, because the way they work is the strangeness, whatever the quarkness is paired with the charge. So if it's a negative charged quark, the quark has a negative amount of whatever its quarkness is. Does that make sense? So a strange quark has -1 strangeness, but an anti-strange quark has +1 strangeness. And it also has positive charge. So yeah, they're all 2/3 or -1/3 amount of charge. And then, yeah, there's topness, charmness. I think charmness is just called charm. It's kind of like I don't know.
Yeah.
The amount of its ness is charm.
Yeah. So that's all of, okay. So we just said 12 particles. 3 of those things, I guess really are your everyday life. That's everything that you touch, interact with. And then, outside of that, we have this whole other set of particles called the bosons. Yeah,
so we covered the fermions. Now it's onto the bosons, which are separate things. They're usually called like force carriers is one way to say them. But yeah, the 3 fundamental forces that are covered in the standard model, there are particles that basically make that force happen. So the simplest one, the one that we've known about the longest, the electromagnetic force, that's an interaction between charged particles. So anything that's charged, the electron, all of the quarks are charged. They all interact through electromagnetic forces. And the force carrying particle, we say, is the photon, which usually you think of as light, but in the standard model, that's the thing that's zipping back and forth between charged particles that causes electromagnetism to happen.
So I think this is something we can delve deeper into, in a future episode. But yeah, there's an interesting structure to the standard model in that we categorize these things as quantum field theories.
Right.
Where you don't have the same field that you learned in your undergrad physics class with your electric field or your magnetic field or whatever it is. Mm-hmm. They've now start describing the fields as an exchange of virtual particles.
Right. Yeah. So a lot of this stuff is covered in, maybe you've come across little squiggly lines with arrows connecting them. And the basic interaction mechanisms are outlined in what are called Feynman diagrams. So Richard Feynman came up with a clever way of just organizing what the diagrams represent, which is complicated integrals. And he just kind of is like, well, just draw pictures. Here's an electron. Here's a positron. Those are charged particles. Draw a little squiggly line. That's the photon interaction between them. And they can repel because they get close together. A bunch of photons go back and forth, and then they diverge. They spread apart. And so that's the representation of the interaction. A little photon is exchanged between the electron and the positron.
And roughly, that's QED in a nutshell.
Yep.
Quantum electrodynamics.
Mm-hmm. Right. Something that's interesting, you just brought up QFT and QED. QFT being quantum field theory. In quantum mechanics, before QFT, like sub-QFT, the particles are assumed to just be in existence. Like you do get into creation and annihilation operators, but it's kind of brought up in the harmonic oscillator, like you're stepping up and down energy levels. But the particles that are talked about in quantum mechanics, like they exist. They exist before you start attacking them with quantum mechanics problem-solving abilities, right? There's no generation of particles or annihilation of particles. But QFT now brings in the mechanics of like, basically, where do those particles come from? How did they get there? How do they interact with each other? Even before they exist, there's something. Maybe it's vacuum, but that's still something that you got to talk about and describe. And then all of a sudden particles exist somehow. And then you can do normal quantum mechanics if you want. But QFT is all about the fields of particles and the potential for there to be particles. And that's what they're talking about. The F part, the field part, are these particle fields. And so particles don't just, they don't exist before you do quantum mechanics in QFT. QFT actually talks about the generation of these particles.
And one thing I learned that I didn't quite understand is, until I started reading this, is that my understanding is that quantum field theory, QFT, is not like, it's not like a theory necessarily in its own right. It's more of a structure that other theories fit into. Mm-hmm. Like quantum electrodynamics is a type of quantum field theory, or quantum chromodynamics is a quantum field theory.
Right. And I think in a later episode, we'll definitely get into that, and we'll get into talking about the different types, the way those field theories came about, basically through Lagrangian mechanics. It's pretty interesting. I don't know. I thought it was less complicated than I thought it was going to be, and way more. I don't know what I say logical, but I could follow it way better than I thought I would be able to.
Well, I think that's the beauty of Feynman, right?
Yeah, probably. But even before him, I mean, I was reading a Griffiths particle physics book, and he goes through like, here's the Maxwell field, which we knew from like basic quantum mechanics. And I guess I was doing field theory before I knew it was actually field theory, but it's stuff I had seen. I'm like, oh yeah, I remember this stuff. And he says that. He's like, you might recognize this as your electromagnetic field equations. I'm like, oh yeah, nice.
So, okay. All right. So we're at bosons still. We got this list of them. That they are these force carrying or interact particles that we kind of been talking about, but there's two types of them, right? There's these gauge bosons and scalar bosons. There's an S there, I guess. Yeah. So we said there's the photon, which is the particle that's going to interact with the not electroweak force, but the electromagnetic only, right?
Yeah, that's right.
And then beyond that, you have the gluon, and this is the force-carrying particle of the quarks of color, I guess. So anytime you have, like with the photon is the thing that interacts between stuff that have electric charge. The gluon is the thing that interacts between things that have color. And then, did you have anything more you wanted to say? I feel like these are a lot more simple to talk about.
Yeah, the photon and gluon are pretty straightforward. Kind of. I still want to learn more about the gluon. There's stuff I don't really get. But the gluon and photon are both massless, which means they both travel at the speed of light only, which, photon, we consider light. It's the speed of the photon is the speed of light, thankfully. And yeah, the gluon also happens to be massless. And we said that these are bosons, which mean they have integer spin. And the integer of gluon and photon spin is 1. Actually, all of the gauge bosons, the spin is 1. But yeah, gluon and photon, 0 mass, 0 charge, spin of 1. Yeah, I think that's it. For gluon, so gluons interact with things that carry color. Photons interact with things that carry charge. The photon itself has 0 charge. The gluon has color. So the gluon can interact with itself, which is kind of strange, different than the photon. So gluons theoretically could group together into a color singlet of red, green, blue gluons and form what's called a glue ball. And it can bunch together gluons in theory. And no one's observed it, but there's no physical reason why it shouldn't happen every once in a while. So here's the weird stuff. A lot of this comes down to group theory and like counting combinations of things and like different basis states, kind of. It's a lot of linear algebra, but I don't completely understand, but somehow 3 colors of gluons leads to 8 possible basis states. So a gluon can be one of 8 types.
Does that include anti-colors as well? Because gluons can be red, green, blue, or anti-red, anti-green, anti-blue.
I think you're right. So I guess it's 6 technically, like 6 colors, quote unquote. But for some, that's what I don't really know, and what I wanted to look more into was why it ends up being 8.
Yeah. So I think this is the type of thing where in the next, in the coming weeks, we're going to learn more about it. This is a learning process for us as well. And, as we learn more, we'll try to enlighten you more. Right. Yeah. And I think, you said, I think probably the most interesting thing, at least so far, about the bosons is the photon is non-interacting with itself because it doesn't carry charge, but the gluon does carry the requirement for interaction of a color. Mm-hmm. And then I think the next interesting thing, the particles that interact with the weak forces, they're, in that case, if you just heard I said particles, is that there's 2 of them.
Right. Well, there's almost 3, but yeah.
Yeah. There's the W plus, W minus, and the Z bosons.
Right. And the plus minus refers to the W. There's a positive version and a negative version of the W particle. I don't think they're antiparticles of each other. Like, I think they're actually separate normal matter particles. And there could be an anti-W plus. I don't actually know, but I think that's true.
Yes, this is something I need to learn.
Like, I don't think there's the W, like, there's the electron, but then there's the anti-electron, which is not in the standard model. I mean, it is because it's the antiparticle, but they don't list it, right? But the W, they do list the W plus and the W minus as separate particles. I'm pretty sure. Obviously, they're very closely related, same exact mass, different charge. But I don't know if they're antiparticles of each other.
Yeah, I don't think so. I mean, I might venture a guess to say no, just because, in our general table, we don't really list too many antiparticles. Mm-hmm. It's just here's the standard particles, and you know that there's an antiparticle for a lot of these things.
Right.
And I mean, I guess we should say though, right? There's like the photon though is its own antiparticle, right?
Right.
So it's not like there's not antiphotons. There's just photons that can annihilate with other photons.
Right. A quick Google brought up that they are antiparticles, but neither of them is like the normal particle. It's just if you have a W plus and you need an antiparticle of it, you get the W minus. If you have a W minus and you need the antiparticle, you get the W plus.
Okay.
But there's not like one is the normal one and one's the anti one, which is kind of interesting.
Which there actually have been some interesting choices there. I know with the neutrino and antineutrinos, with I think it was Gelman who made the choice to call which one the antineutrino and which one the neutrino.
Right. Yeah, exactly. So they're all the same. It's just kind of up to someone to say this is the one and the other one's the anti.
So I don't know too much about these sets of bosons. I'm still reading on bosons, really. The
most interesting thing I found, and it actually comes up in the quarks a little bit too, but it's more strongly represented in the weak bosons, W and the Z, is that the particles, like the theory comes down to, how do I want to say this? Imagine like an X and a Y coordinate axis. And say that's the W and the Z boson. But it's not. The X and the Y coordinate axis are other theoretical particles in the theory, and then rotate the X and the Y, and you get a mix of X and Ys, which makes up the actual particles that we observe. And there's a particular angle that we rotate the X and Y axis through, and that's what the particles that we actually see are represented by that angle. So there's some other states that exist in theory, and then the observed particles are like a linear combination of those.
Interesting.
Yeah. I think it's called the Weinberg angle. Yeah, the Weinberg angle, or the weak mixing angle.
That would make sense.
Oh, I'm sorry. It's the photon and the Z. That's where the electroweak theory comes in. That's how they're, one way, I guess, that they're unified, is that you take these two fictitious particles, the B0 and the W0, and then have those be X and Y axes, and then rotate them, and then you get the photon and the Z0.
Huh. That's really weird. You almost wonder, like, wait, why do we have to invent these other particles if it's a pure rotation?
Right. I don't know. I mean, I'm reading The New Cosmic Onion. It didn't give many details on that. But yeah. There's a lot of this kind of like weird mixing where it's not like the particles aren't actually pure. Like, I guess this is an extreme version of something that happens in all the particles, where like the charmed quark is slightly a strange quark. Meaning like every once in a while where you expect a charm, you'll just randomly get a strange. And it like breaks all the conservation rules, and it's just, nature is just like, whatever, we're mostly charmed, but you're kind of estranged sometimes. So there's all these little angles that are like slightly mixed. And actually, one place they're looking to expand the standard model is that the proton being the lowest mass way for the quarks to arrange themselves, proton is stable. And they don't know for sure if it's stable, but it is if there's no mixing involved. But there might be some slight mixing between the quarks and the leptons. And if that's true, there's a possible way for the proton to actually decay every once in a while. We've never observed it, but it's possible. And if the proton ever did decay, then that would open a whole new door. It wouldn't really make the standard model wrong. It would just say, okay, there's actually a connection between quarks and leptons that we didn't know existed before. Again, through one of these mixing angles that's slight. But in the in the weak interaction, that angle is huge, we just notice it a lot more.
Cool. So, okay. So I think, for now, that's pretty much all I want to say about the gauge bosons. I guess there's one other thing we might mention, and that's the elusive graviton.
Right. Yeah. So if the standard model is all-encompassing, meaning it encompasses all elementary particles and all forces, there's a glaring gap in that there's no gravity in it. So they try and extend it and introduce a graviton, which would be the quantum particle for gravity. But it's just kind of, they don't know how it works. They don't know where it goes or what it is, but it should be there. If this model, if a model has has all of physics within it, there should be a gravity particle.
Yeah. It's just, each force should have a boson or bosons related to it. So, we know of the electromagnetic force, weak force, strong force, have all those ones. So we just are continuing, we're extrapolating that trend and saying, okay, there must be a gravity particle. If we haven't seen it yet, we'll call it the graviton.
Right. Yeah. And, most of the time people talk about how weak the gravitational force is. And that's actually an explanation as to why we don't see any quantum gravity effects, because these other forces are so much stronger in any sort of experiment we could ever want to run in a laboratory that it's just completely, basically way, way, way below the noise of any experiment we would want to run. That is, gravity is just way below the noise. Like any interaction is just going to completely overpower the gravitational interaction. There's nothing we can do to completely isolate and get a gravity interaction experiment to happen.
That's not to say people aren't trying.
Yes, true. But that's the main reason. It's just the gravity is so weak that it's just try and do a gravity only experiment and you're just going to have so much electromagnetic force, so much weak force, so much strong force happening at the same time. It's just, you can't isolate the gravitational force.
Right.
So yeah, those are gauge bosons. And hopefully at some point we'll get into what the word gauge means. And that comes into those Lagrangian field theories that we were talking about a little while ago. But the different type of boson, which is not necessarily a force particle. So far we have 6 leptons, 6 quarks, 4 bosons, and then we got a 5th boson, which is under the category of a scalar boson, which is finally the Higgs particle. Yeah, drum roll. The Higgs. We got the Higgs guy sitting all by its lonesome. It's got a pretty big mass. It has 0 charge. So remember, it's a boson, so it has to have integer spin. The integer spin of the Higgs is 0. So it actually has 0 spin. Sometimes the gauge bosons are called vector bosons. And actually, I think the W and the Z are called intermediate vector bosons.
Yes.
Yeah. So, yeah, we got... Is that true? Yeah, I'm pretty sure that's true.
Yes, that is true.
So vector meaning it's got a spin of 1, which in physics we treat as a vector that points in a certain direction and can align different ways. But at spin of 0, there's nothing to point. So it's just sitting there. It's a point. It's a scalar.
Right.
Yeah.
And, this is the one that we built the LHC for. Mm-hmm. This is the one that was discovered in 2012 and that you've probably heard everywhere. It had another name that I don't really want to say here, but it was a horrible name to give, that the media gave this particle that I think caused a bunch of the stir with it.
Wait, what was it? Now I don't know.
I don't want to credit it with that name. We're just going to leave it as the Higgs. I'll tell you afterwards.
Is it a bad word?
No, not at all.
Oh, I know. Okay, I know what you're going to say. Yeah. Yeah, we won't continue that. Let's let it die.
Yes. Okay, thanks. But so this is, the newest addition to...
It's the last one, the one that they knew existed, but they didn't know what its mass was. They hadn't observed one.
And I mean, this was one of the, really cool parts with standard model, kind of like how we started talking in the first place, is Peter Higgs predicted this was going to exist in, I think it was like the 70s, a long time ago. He was able to define all of the properties something like this should have, including the mass. So that led us to know the energy that we needed to go up to.
Right.
And the only thing that stopped us from finding it, and the reason it took so long, was just time and money, and technology, I guess.
Right. Yep.
But, lo and behold, he made that prediction so many years ago. 64 is when it was. And, there you go. He predicted it. 50 years later, we found it.
Right. Smack dab right in the middle of what people expected its mass to be. Yeah. So most of the particles we've been talking about have been the heaviest quarks around a few giga electron volts. The W and the Z bosons are pushing 100 GeV. And then they're just a little shy. The Z is about 90 GeV. And the Higgs is at 125 GeV. So it's a pretty massive particle. There's a heavier quark, the top quark, as I said before, but it's so short-lived, the physics that you can get from it, there's not much to glean from a top quark. It basically disintegrates into a lighter quark pretty quickly. And same with the Higgs, but that's, it's important enough, I guess, that they spent a lot of time setting up experiments to exactly measure the Higgs, even though it decays very quickly. Basically, the higher the mass, the less stable and the more quickly the thing's going to just completely annihilate itself.
Yeah, because it just wants to go to...
I shouldn't say annihilate, decays.
Yeah, it wants to be in the stablest, lowest energy it can be, and anything wants to be there.
Yep.
Which I think that's pretty much that's a description of all of physics.
Yeah, right. Trying to get to the bottom.
Yeah, I think the maybe thing to note is I don't know. This is kind of my pop science view of the Higgs boson, is that it's different in that this is the particle that we think gives other particles mass. Is that right?
Right.
Do you know?
Yeah, it's quote unquote the Higgs mechanism, which is all I know about it. It's called that. That's how they get mass, essentially. But it's the Higgs field, and things interact through the Higgs field, and it kind of makes stuff not travel at the speed of light. It makes the gauge bosons, or the intermediate vector bosons, the W and the Z, be messy, way messier than they should be. It makes all the particles split in these weird ways that otherwise they would be identical, except they have different masses. So a lot of times they say it breaks the symmetry of the systems. When, what's different between the three generations? You have up and down, charm and strange, top and bottom. Up, charm, and top are identical, except they have different masses. Down, strange, and bottom are identical, except they have different masses. Electron, muon, and tau are identical, except they have different masses. So if the Higgs mechanism was gone, all three generations would just collapse down into one, essentially. We wouldn't have as many particles as we do.
So thank you, Higgs boson.
Thanks.
Making our life complicated.
Yeah, exactly.
So that, in an hour and a half, that was roughly the periodic table, I'll call it maybe, of elementary particles. Mm-hmm. That's all of the particles and all the forces that are encompassed by the standard model.
Right. So where I'd like to go from here next time is talking about what we do when we start combining quarks. So we'll get into those hadrons, the bosons and the mesons. And I'd like to get into some Lagrangian physics and where these bosons come from and how they pop out of the theory. Get into some fun math stuff with Lagrangian mechanics of fields, and then lastly get into some extensions of the standard model. Like, what are people thinking beyond this very nice compact succinct theory or group of theories. Like what else could we do? What are people looking for? And so we'll talk about supersymmetry and some other things like that.
And then a few other things I'd like to add in our discussion is that I think there's some interesting history and background we could go into with the electrons and the positrons.
Okay.
And that's a good lead in as well for, some of the Lagrangian type stuff you were talking about. Wherever we cover that, we can do that. But, QED and the, Feynman's kind of path. It's not a path integral. What's the name of his interpretation of this? The where you take all the roots and you sum them all up.
QED?
Yeah.
I don't know what else it's called.
I think I thought there was a name for that in general. But
renormalization? Is that what you're talking about? That's not really. I mean, Feynman's there, but yeah.
Yeah, no, but no, I thought there was a name for when you consider kind of like the Fermat's principle. Mm-hmm. There's a name for that sort of idea where you take, okay, let's assume we're going to go over all of the paths.
Like all possible virtual particles and stuff like that.
Yeah. But maybe I'm forgetting. I don't know. Mm-hmm. And then also I think a couple other areas that we could touch is kind of where the standard model breaks down and leaves some stuff empty. Because it's, as great of a theory it is, there's definitely other physics out there that is it doesn't encompass, that is very strange and leads to a lot of interesting questions.
Mm-hmm. Yep. Cool. Yeah, well, I enjoyed this and I'm excited to go into it a little deeper in some parts. I enjoyed just researching this, looking into it.
Yeah, I mean, it's a really rich and deep field that, there's no way we're going to be able to cover it all in a few podcasts, but I'm just hoping, by the end of this, I'll know more, you'll know more, and hopefully anyone listening will also have, slightly better understanding of, their world, their universe.
Right. Well, cool. Sounds good. More to come on the standard model next time.
All right, great. Thanks for listening.
Mm-hmm.